This is the first video in a series of 2 in which we explain reversible isothermal gas expansions. Okay, so this is the setup that we have to explain these reversible isothermal gas expansions. We have a gas inside a cylinder with a movable piston, and this gas is under some external pressure caused by this mass, which is resting on this tray that is pushing the gas in. Okay, so then what we're going to do is just try to remove this mass, and then what will happen is that the external pressure will drop, and then the gas will be able to expand against that vacuum. Right, so something that is important in this expansion is that the temperature of the gas will not change, so that's why we call this isothermal. And that actually means that because this is a gas, and the energy of the gas, an ideal gas, only depends on the temperature, then if the temperature doesn't change, the energy of the gas will not change, and that means that according to the first law, heat will be equal to the minus work. Okay, so that is one of the characteristics of an isothermal gas expansion. Okay, we also have some other properties here. The number of moles of the gas is N, the temperature is T, which is these two things stay constant. Then initially, when we have a mass that we're going to call M1 resting on this tray, okay, the volume will be V1, and then the pressure will be P1. Okay, those are our starting conditions there. Now, what we're going to do is calculate the work done once we remove this mass according to 3 different processes. In the first one, we're simply going to remove M1 directly. Okay, so we're going to go from a mass of M1 to no mass resting on the tray. Okay, then that would be one step. But then in the second process, we're going to go from M1, and then instead of removing the mass entirely, we're going to remove a part of it and simply leave just 1/4 of the initial mass left and 1/4. But then after that, we will remove that 1/4 of the mass that you had entirely and see how the gas continues to expand. So that will be a 2-step process, and then we're going to do a 3-step process in which we go from M1. We simply are going to remove half of this mass initially, so that will give us M1 halves. And then we're going to remove half of that mass, so that will give us M1/4. And at the end, we're going to just remove all of the mass entirely, so that the gas can expand. Okay, so notice that the initial points and the final points in all these 3 processes are going to be the same. We go from mass M1 to no mass, right? Because this mass is causing the external pressure. If you're reducing the external pressure, what the gas will do is expand, and then we can calculate the work. Okay, so that's kind of the setup for this. The idea here is going to be to explain how work changes according to the pathway that you take in this expansion. Okay, something that is very important here is to recognize that we're letting the system reach what we call mechanical equilibrium. Okay, so look at this first point. What we have right here is that gas has some pressure, right? So it's actually pushing the pistons towards the right, okay, with some force. But because the piston is not moving, that means that there's a force that is opposing that force by the gas that has exactly the same magnitude. And that force that is opposing the pressure exerted by the gas is the pressure exerted by this external mass, right? So that's what we call mechanical equilibrium. And then when you have mechanical equilibrium, what that means is that the external pressure of the gas is identical, or the external pressure is identical to the pressure of the gas. Okay, that is what's going to happen. So whenever we do these steps, we're letting the system reach mechanical equilibrium, right? So from here, once we remove a little bit of the mass to leave just 1/4 of the mass, we're letting the system equilibrate so that the external pressure is identical to the pressure of the gas at that particular point. And the same thing will happen here. Okay, so, all right, so a couple more things about the external pressure before we get started. Notice that the external pressure here initially is going to be equal to P1, okay, because you have a mechanical equilibrium, and P1 is the pressure of the gas. But this is also equal to the force that this mass is exerting over the area, which is just the area of that piston. Okay, but the force is equal to M1 times G over the area, right? That's just the gravitational force exerting that force over an area that is the area of the piston. Okay, so that is our initial external pressure, okay, when the two pressures are equal, and then that is equal to the pressure of the gas P1. Right, so now we're actually ready to start to do these expansions. Right, let's go to the first one. Right, so what we do is we take this mass 1 and then just remove it entirely. Right, at that point what happens is that the external pressure then will be 0, okay, because there's no mass left. If we consider that this rope and the tray are massless and the piston is frictionless, it can move without any friction, then if you remove entirely the mass that you have right here, then there's no external pressure at all. Okay, when you try to calculate the work for this particular expansion, then you will have that, well, work is equal to minus the product of the external pressure times the change in volume. But if you're not pushing against anything, notice that you have a vacuum here, so there's nothing to push against, then work is 0. Okay, so that will be actually our first case. For that particular case, okay, when you remove the mass entirely, the gas can freely expand, nothing is opposing it, and what that means is that you're actually not doing any work. Okay, so that will be the easiest of these three paths. Let's then calculate the second one, right? So what is the work done in these two steps? Alright, so that's what we're going to be working on now, and we're going to calculate first that first step. What is the work that you do when you let the gas expand, not against M1, but what we do is we reduce the mass of M1 to M1 fourths. Okay, so we're just going to remove this amount of mass and just leave M1 fourths, and then try to figure out what the work there is. Okay, so work is always going to be external pressure over delta V. But notice that the external pressure now is actually solely due by 1/4 of this mass. Right, so notice that what you will have right here is that pressure is M1 fourths, and then if that is the case, then the external pressure will be equal to P1 fourths. Okay, so the external pressure in this particular step will be equal to what we had initially divided by 4, because the mass has been reduced to 1/4 of the initial mass. Okay, so that is our external pressure. Now, what we have to do then is calculate what the change in volume is. Alright, so the initial volume is fairly simple. Notice that we're at the start of expansion, so the initial volume is V1. And the question is, well, what is the final volume? Well, something that we can do here to figure out what the final volume of that gas is to recognize that this is an ideal gas, and if the number of moles and temperature are the same, then this has to apply. Okay? Alright, so we know what the initial pressure is, P1, we know what the initial volume is, V1, and then the question is, well, what is the final pressure of the gas and what is the final volume of the gas? Well, notice that what we have here is that once you remove a little bit of the mass that you have right there to leave just 1/4 of the mass, right, the external pressure is dropped. Okay, at that point, the internal pressure of the gas is much greater than the external pressure of the gas, and the gas will expand because this pressure, the pressure with which the gas is pushing that piston, is actually larger than the external pressure that is pushing in the other direction. Okay, but as the gas expands, the volume increases, and then the pressure of the gas drops. Okay, so eventually the pressure of the gas will drop enough that it equals the external pressure. And at that point, when you have the mechanical equilibrium after the expansion, okay, when the internal pressure of the gas has equaled the external pressure against which it's pushing, then the expansion will finish. Okay, so what that means is that the final pressure of the gas at the point where you reach mechanical equilibrium is equal to the external pressure. And we know what the external pressure is, which is P1 fourths, so we're actually ready then to solve for the final volume. Okay, so notice that the final volume is going to be equal to 4V1. Okay, this is fairly simple to see. Notice that the final pressure of the gas is going to be 1/4 of what you had initially. That means that the volume must have quadrupled. Okay, so that's exactly what we have right here. Okay, great. So now we have the external pressure, the initial volume, the final volume for only this step. So we're actually ready to calculate what the work is. All right, so notice that the work is going to be equal to minus P1 fourths, okay, which is the external pressure, multiplied by the change in volume, which is 4V1 minus V1. right? So you have inside the parentheses 3v1, and then you have to multiply that by minus p1 fourths. So notice that this is going to be equal to minus 3/4 p1 v1. Okay, that is the work that you do in this first step. Okay, let's take a look at the second step then. Right, so now you have simply m1/4 left, that little piece, and then you're going to remove it entirely to let the gas to continue to expand. But in that case, again, if you remove all of the mass, then there's no external pressure at all. And what that would mean is that the work that you do in this second step is zero. You're not pushing against anything. All right, so we have now the work in these two steps. The work in that step is zero. You're not pushing against anything. The work in this step happens to be minus 3/4 p1 v1. So we know that in this second process, we have that work that you have done is 3/4 p1 v1. Okay, now this is very interesting. Notice how work depends on how you do the process. We've done the process two different ways. First, removing the mass entirely, and second, doing two steps. Not removing the mass entirely, but just a little bit of it, and then removing the little bit left over entirely. The work in both is actually different, and that actually tells you that work is a state function, okay, because it depends on the path. The energy is not a state function. Notice that the change in energy is zero in both, okay, because the initial state and the final state are the same in these two expansions. Okay, so just to corroborate that work depends on the pathway that you take, we're going to do one more process in which instead of taking two steps, we're going to take 3 steps. And then let's see how the work there will be. All right, so the questions are going to be like this. Okay, notice that now we have to calculate the work in 2 steps. This step, that step, and then that step. This one is going to be very easy, right? That will be the step in which, well, you have a little bit of the initial mass left, but then you remove it entirely, so you're not pushing against anything. And what that means is that the work in this step will be zero. So this we're not even going to talk about. We just have to figure out what the work in that step is, and then add the work to that step. All right, so let's go to the first one. Again, notice that the work is always going to be external pressure times the change in volume. And this is the first step, right? So what we're actually doing is taking this M1 mass and then dividing it in 2 pieces and removing one of the mass, one of the halves of that mass. Okay, so then what we actually have here is that, well, the external pressure is going to be not M1, but now we're going to have only half of that mass. So the external pressure is going to be 1/2 of this, which means that it's going to be 1/2 of P1. All right, so the external pressure in this first step is going to be P1/2. Okay, the initial volume. Well, we're at the start of the expansion. Okay, so the initial volume is P1. And the question is, well, what is the final volume? And again, for this, we always do the ideal gas relation. Okay, initially we have P1, V1, and at the end we have the final pressure and the final volume. Again, much as before, this gas, the final pressure of the gas is going to be limited by the moment in which the external, the pressure of the gas equals to the external pressure. Well, since the external pressure is equal to P1/2, then the final pressure is also equal to P1/2. And that means that you know what the final volume is, right? P1 cancels with P1, and then your final volume will be 2V1. Makes perfect sense. You're having the pressure, that means the volume has to double. Okay, so then we're ready to actually calculate what the volume in this expansion would be. The external pressure is P1/2, and then the final volume is 2V1. And the initial volume, of course, I made a mistake here. That is not P1, that is simply V1. Okay, those are volumes. The initial volume is going to be simply V1. Okay, so then we actually know what the work in this first step would be. Notice that here you have V1 inside the parentheses multiplied by minus P1/2. The work there is going to be equal to minus 1/2 of P1 V1. All right, that is that first step. Now we have to worry about this second step, but this is going to be straightforward because we know how to do this quite well. The changes. Now we take the half mass that we have left, and then we just remove another piece to just leave 1/4 of the initial mass. If we have 1/4 of the initial mass, then the external pressure is going to be 1/4 of P1. Okay? Now your initial volume here will be V1, 2V1, okay, because you're now at the point where you have left this expand to double the volume. Okay, so your initial volume for this particular step will be 2V1, and the question is, well, what is the final volume? Well, you come to the expression, the final volume is going to be such where this is what you get, and then your final volume will be 4V1. Okay, so then we have everything that we need in order to calculate the work in this second step. External pressure, 1/4 of the initial one. Final volume, 4V1. Initial volume of that step, 2V1. Okay, so when you calculate this, what you get out of this is equal to -1/2 P1 V1. Okay, so in this step, you also have -1/2 P1 V1. All right, the work in this step, we said that is 0, so then we actually already have what the total work in this 3-step process will be. That total work is going to be the sum of this, that, and that, but this is exactly minus P1 V1. Okay, so then we have now the 3 works that we wanted. We have this expansion 3 different ways. One of them will remove the mass directly, entirely. And the work there is 0, you're not pushing against anything. The second way, we first have removed 3/4 of the mass and left just 1/4 of the mass, and let the system push against that. Once you reach a mechanical equilibrium, you remove that mass and let it expand completely, that's that. And the work that we get out of there is just -3/2 P1 V1, larger than what you get initially. And then we have done the expansion 3 in a different way, right, with 3 steps. First we remove half of the mass, then 1/4 of the leftover mass, and then the other 1/4 of the mass. And then what we find is that in these 3 steps, the work that you get is minus P1 V1. So something that is very important about this is that it seems like the more steps you have, okay, the more work you're doing, okay, which is something very important because work is useful. And we always want to try to extract as much work as possible from a process. Okay, so it looks like the larger the number of steps that you have, the more work you can do. Okay, so this kind of sets up the idea of what a reversible isothermal expansion process would be, which is just an idealized process in which you're simply letting the expansion go by removing very little amounts of mass from this tray at a time, so that you can actually get the maximum possible work. The mathematics and the physics of how to do that are going to be explained in the next video.